Let us see the practical oscillator circuits. The transistor oscillators used in electronics are Colpit's oscillator, phase shift oscillator, crystal oscillator, Hartley oscillator, wine bridge oscillator, and tuned plate oscillators. So these are some of the circuits used in electronics to produce the electrical oscillations or to produce AC voltage. Now let us see one by one the working and circuit diagram of these oscillators. So firstly we consider the Colpit's oscillator. The Colpit's oscillator is again a very high frequency oscillator because some of the oscillators like phase shift oscillators are used to produce low frequencies. So in electronics we require low frequencies as well as the high frequencies depending upon the use of that oscillator. So here the Colpit's oscillator is basically high frequency oscillator, means by using this Colpit's oscillator we can produce the AC voltages of the order of megahertz, and therefore it is called as high frequency oscillator. So this is the circuit diagram for Colpit's oscillator. The basic requirement for oscillator is a tank circuit which produces electrical oscillations. The second requirement is an amplifier which increases the amplitude of the weak electrical oscillations produced by a tank circuit. And third important requirement is the phase shifting network or a positive feedback. So let us see how these three conditions are satisfied in this circuit. So from the left hand side we see that this part in the circuit consists of single stage common emitter amplifier, which we have studied in amplifier chart. So here R1, R2 are the biasing resistors. RE and CE provides the stability to the operating point. CI and C0 or CO represents the coupling capacitors. And here we used only single transistor Q1. Therefore, the left hand side marked with red color represents single stage common emitter amplifier. Now if we consider this right hand side or this part of the circuit, this forms a tank circuit. As we have seen that tank circuit is the parallel combination of the coil L or inductance L and capacitor C. So here we have used two capacitors C1 and C2 across this coil L, and the center point of these two capacitors C1, C2 is grounded. Now let us see the working of this circuit. The frequency of oscillation is given by F is equal to 1 upon 2 pi root LC. I will discuss it on later part. So when we switch on the circuit, means we provide DC power to this circuit. What will happen? Through this path, the capacitors will charge with polarities as shown in figure like this. C1, this is positive, this is negative. And for C2, this is positive, this is negative. Therefore, this point effectively is 0. Or if we think of the point P in the circuit and point Q of the circuit, then we see that there is a phase difference of 180 degree between point P and point Q. That is very important because overall phase shift in the circuit must be 0 or it must be 360 degree. Then and only then there exists a positive feedback. So we should provide the positive feedback. That is the first requirement. The secondly, the Barkhausen criteria, that is A beta is equal to 1 must be satisfied, and the feedback signal which we have given to the base of the transistor must be of proper phase. So if we connect the tank circuit in this fashion, then it will satisfy all these three conditions. So when we make the switch S1 on, the capacitors C1 and C2 get charged with this polarity. See here, this is positive, and here the lower plate of C2 is negative. Therefore, P terminal is positive and Q terminal is negative. So there is a phase difference of 180 degree between point P and Q. The voltage across C2 is fed back or is given to the base of the transistor via Ci. So part of the output energy is given back to the input of the transistor, and the output voltage developed in the collector of the transistor Q1 is used to again charge the capacitor C1 and C2. So whatever amount of energy is lost by C1 and C2 is provided by the transistor amplifier, so that the proper charging of capacitor C1 and C2 takes place. Now let us see about the phase. This is positive. This point Q is 180 out of phase. When this signal or this voltage come to base of the transistor again produces 180 phase shift. As we have seen that in case of common emitter configuration, there is a phase difference of 180 degree between base and collector. See, when the signal goes from base to collector, it gets amplified, as well as there is a phase difference of 180 degree. When this voltage comes to this tank circuit, it again produces a phase difference of 180 degree. So total phase difference in this loop is 360 degree, and therefore there exists a positive feedback, which is the requirement of any oscillator. And this circuit produces the output waveform, which is a sine wave. So all these oscillators like Colpit, phase shift, crystal oscillators, all these are called as sinusoidal oscillators, because the output waveform of these oscillators is always a sine wave, and therefore these oscillators are called as sinusoidal oscillators. Now let us see the expression for frequency of the produced AC voltage or AC waveform. The frequency of oscillation is given by f is equal to 2 pi root LC. Here L is the value of self-inductance of the coil measured in Henry. C represents the equivalent capacitor of C1 and C2. As in previous diagram, we have seen that we have used the two capacitors C1 and C2. Therefore, the effective capacitor C1 and C2, the effective capacitor between point P and Q is equal to C is equal to C1 C2 upon C1 plus C2. So you have to use this value of C in this formula 1 upon 2 pi root LC. So we can design a Colpit's oscillator to a desired frequency by selecting proper values of L and C. The oscillations or AC voltage produced by the Colpit's oscillator has high frequency in the range of megahertz. Therefore, Colpit's oscillator is a high frequency oscillator. Now, what are the advantages of the Colpit's oscillator? The Colpit's oscillator is used in commercial signal generators. You might have used signal generators in laboratory. You have performed one of the experiment Lysage's figures, and in that we use a signal generator in the laboratory. So that signal generators can also be designed by using Colpit's oscillator. Usually in high frequency induction heating applications. So in industry, we can melt the materials by using induction heating. What is the induction heating? Simply, just like you might have heard about micro oven. So same type of application. So in industry, we take the material in a crucible. Here you take the material which is to be molten. A coil is surrounded around this crucible, and high frequency AC voltage is applied to this coil. Due to this high frequency signal, what will happen? the melting of the material will take place. And this type of heating is called as induction heating. We produce the magnetic field, and by using that we can heat the material and it can be molten. So this type of arrangement is used in industry to melt the materials. So that is called as induction heating. It is also used in the radio and TV receivers as a local oscillators. In radio receiver also there is a oscillator section, and that is designed by using Hartley oscillator. Now what is the disadvantage? It uses inductance, that is the disadvantage. Because when you are designing a inductor, you have to consider the number of turns of that inductor, because in designing the proper frequency, you should have the proper values of L and C. So that is the drawback of this Colpit oscillator.
If you like this video, don't forget to subscribe, comment and share this video with your friends. Thank you for watching.